you. My name's McDonald. I'm an engineer at Google. I spent most of my career kind of doing like user-facing apps for the most part. A lot of web development, bit Android development. A couple of years ago, I did a rotation through the Google Brain team and learned all about machine learning. So ever since then, I've kind of been interested in that intersection between machine learning and like JavaScript front-end frameworks. So if you ask somebody, or if somebody asked me, I didn't know anything about software development, wanted to get into it and become a ML engineer of some sort, and I asked, what language should I learn to get started in machine learning? What would you say, right? Most people would say you should learn Python. That's the kind of gold standard for machine learning. But I want to challenge that today. I think that the browser and JavaScript in particular is going to be a contender in the coming years. There's a lot of good reasons for that. Has anybody seen this demo before? This app? Yeah, a couple of people. So this is a tool that we've built for educational purposes, really. This was designed to show people how a neural network learns and how it works, purely as an educational tool. We use it in some of our own courses. We get emails every now and then from professors outside around the world who thank us for writing this thing, because it's a fantastic little visualization. And it's been wildly successful, but why has this been successful? I think the big reason is because it works in the browser. So why is browser-based machine learning so attractive, in my view? I think the barrier to entry is a big one. There's a really low barrier of entry for a browser, right? Like, if you want to share your app with somebody, you share a link, and they can load it, almost guaranteed, right? Whether it be on a phone, or whether it be on their laptop, or desktop, or anywhere in between, right? Even your TV. There's no kind of security concerns when you load something up in a web browser. There's no permission dialogues. There's no app store you have to go through to get something loaded up. You can just click a link and you're good to go. It's interactive too. So a web-based, the web API, I guess, is built around this kind of human interaction. It's really easy to draw things, to animate things, make it look good, and handle events, compared with something like Python or a shell script or a Jupyter notebook or something like that. Because of this, it's quick, right? Like, all the code happens on the client, and so the important, I guess, performance aspects of running a UI app, it's really quick. So sensors are a big thing, right? Like, if machine learning is fueled by data, then sensors in devices are like a drug to machine learning models. You've got all dozens and dozens of sensors that are available on all mobile devices. Not so much on desktops. I've got a few, but not as many as the mobile device. But these things are available with really simple APIs. There's a couple of lines of code to pull this stuff up, and you can get this data in real time. There may be permission dialogues for some of it, but this is really quick. You can find out where someone is. You can find out what they look like. You can listen to their voice. You can find out the temperature around them. You can translate audio and a bunch of other stuff. The last point that I think is quite important is that the data stays on the client. So technically, this is really useful because having it on the client means you don't have to do a round trip to the server. And so if you want to build a performant application, it's it's super fast. You don't have to worry about sending it to the server or off to the cloud. But from a policy point of view as well, user data is sensitive, right? You need to treat it with care. You can't mess around with it. You can't just throw it into log files. There's a lot of extra work has to go into just handling someone's data. And you might not want to do that. Legally, you might not be allowed to do that. So having the data stay on the client, being able to put machine learning on a device without ever processing a user's sensitive information opens up a whole bunch of use cases that previously you might not have been able to do. So how do I do this? How do we get into web-based machine learning? The TensorFlow team has put together an ecosystem of libraries and tools called TensorFlow.js. Before we get into the technical details, I'll kind of show you what it can do. You can author models directly in the browser, so you can train from scratch. So on my TensorFlow Lite, you can load up code, write up your model, and learn in the browser. I'll give you an example of this later on. You can also load a pre-trained model for inference. So in Adam's example, you can download the MobileNet model, load it up in the browser, and use it yourself. And you can do the in-between stuff as well. So like Adam's great example of going through retraining MobileNet, you can do the same thing in TensorFlow.js. You can load up the MobileNet model, and you can continuously modify the model. You can add new data to it, fine-tune it, whatever you need. This is a really powerful technique. I won't thing to talk about it. So if anyone was here for Adam's talk, that was a fantastic explanation. What does the API look like? So in the browser comes standard, right? The user has a browser, they bring it with them. All modern browsers support WebGL. If they happen to have hardware acceleration, like a GPU or something like that, WebGL will use that, but if they don't, it still runs on CPU. So the user brings that with them. On top of that, we provide two layers. We've got the ops API. So this is all low-level kind of mathematical operations like add and multiply, subtract. We also bring a bunch of kind of pre-canned learning algorithms like stochastic gradient descent and Atom. And this is a fairly low-level API. If you want to write all of your models mathematically by hand, you can operate at this layer, or you can go a level up and you can go for the layers API. This is API compatible with Keras. If you ever use Keras either by itself in like a standalone Keras or Keras within TensorFlow, the API is identical. It works with the ops API, but you can kind of choose what layer of abstraction you want to work at, or you can mix the two because they all ultimately just operate on tensors. If you already have models, or you're looking to export or move models around, if you're using the TensorFlow, the TensorFlow core API, sorry, I should have mentioned the ops API is also API compatible with the Python core API in TensorFlow. If you're saving a model there, you'll save it into a save model format, and that can be loaded up into the JavaScript API. If you're working in Keras, you can export in Keras's H5 or whatever it is format, and load it up in the layers API. So I'll give you a quick example of what both of the APIs look like. So in this example, we're going to fit a polynomial. So we've got, let's see, my mouse cursor. We've got y equals ax squared plus bx plus c. In this case, we're going to try and learn what the values of a, b, and c are, given our x data and y data. So it's JavaScript, so we import it. We use the tf namespace alias just so it looks like all the code in Python. We set up the variables that we want to learn, right? This is a, b, and c. Initialize them as tensors, give them an initial value, 0.1. Call variable to mark them as a trainable variable. So this is something that we'll learn throughout the process, and the model will change. And we write up the function. So here we've got f of x equals a x squared times, a times x squared plus b times x plus c. So this is identical to the Python API. If you're familiar with writing TensorFlow code in Python, this is, apart from the triangle arrow and the semicolon at the end, this is identical to Python. One thing that Python has that we don't have in JavaScript is operator overloading. So in Python, you probably wouldn't write this out as like tf.add, tf.add, tf.mul, just because it's verbose. Python supports operator overloading. So you end up writing something a little bit more like this. JavaScript doesn't support operator overloading. So what we've done instead is put chaining. So all of these operations are available on the tensors themselves. So now you can write f of x equals a times x squared plus b times x plus c, which is idiomatic JavaScript. It's much nicer, easier to read, and easier to write, more importantly. And this uses the JavaScript lambda expression format as well. We want to write a loss function. So our loss from our y and y prime is our mean squared error. Pretty simple. Use one of our pre-canned optimizers. In this case, we're using the built-in stochastic gradient descent optimizer. And then just run a few training steps, right? This is a optimizer. We want to minimize this function. We want to minimize the loss of f of x with our labels. Pretty simple, right? At the layers API, we'll give an example using a sequential recurrent network. This is a calculator where we punch in a string of a sequence of characters into an LSTM encoder, some hidden bottleneck, and then a decoder to turn it back into characters. So again, we import it, and this is the Keras API. So if you're familiar with writing in Keras or using the layers APIs in TensorFlow Keras, this is the same thing, right? We're setting up a sequential model. This just means that the layers feed into each other. So the first layer's output is the next layer's input, as opposed to like a raw graph-based model that you could build from scratch. For most purposes, this is all you need. Set up our layers. This is our encoder. We've got an LSTM, some hidden size. What shape is the input? Here's our bottleneck. set up a decoder, another LSTM of some size. This time we want to generate sequences. We're not turning sequences into a vector, we're turning a vector into sequences. And then on each of those sequences, we want to add a dense layer, then activate it with softmax and turn it back into characters, right? Pretty simple. This is a recurrent network that we've just built in, what's that, like 6 lines of code. Compile it. So Keras is exactly the same as the Keras Python API. You can either provide these like strings that map to the built-in loss functions, optimizers, metrics, etc. Or if you need more configuration options, you can build these as objects and then pass them in instead. In this case, we're just using the defaults. So here, we then call model fit on our data, how much we want to do it once. Because this is a long-running operation, this might take 20 seconds. And in JavaScript, we don't want to block the UI thread. We've got a single-threaded model. We use the await syntax JavaScript promises. And because this is just a promise, you can use await, you can use .then, .catch, .finally, etc. And that will give you callbacks once the model's finished. In addition to that, if you need to get updates while the model is training, like kind of per step or whatever, there is another API you can use that will call you back when it yields. We also return the history here, which is how you get access to the accuracy along each step of the training process. Right, so importing existing models. This is a demo. Like the code for this, the code for importing a model is very simple. There's a couple lines of code, so I thought we'd do something a little bit more fun. This is a game that was built by the Google Brand Studio. It loaded up an existing model into JavaScript. They built a game around it. It is basically what it says in the name. It gives you an emoji, and you've got to find it using the camera. I might need some help, so if anyone's got like the thing that pops up on the screen, let me know. This is a random game, so we'll see how it turns out. And this all runs in the browser. See that all right? Computer, sweet. Anyone got a t-shirt? No? Got a t-shirt?
Am I seeing a golf cart? Do I see a restaurant? Might I see a hand block?
No, it's not doing it. Oh. That's machine learning for you, right? Let's see, let's get back here. So as far as machine learning goes, that was a very simple model. Much like this, I mean, technically the steps that they went through to build this model is exactly the same as what Adam just demoed. This is a mobile net model that they have retrained. Like the 1,000 categories in mobile net don't map nicely to the set of emojis. I think that like the ImageNet categories are like there's like 200 breeds of dog or something like that, which there's only a couple of dog emojis. What they've done is they set up labels for I think there's about 110 different emoji. They gathered the photos for each of those emoji and ran the fine-tuning retraining process. Another place to find out more about that is obviously Adam's talk, but there's a code lab out there called TensorFlow for Poets, which shows you how to do it without writing any code. You just run some Python script exactly like it was demoed earlier. And they exported that model, loaded it up in JavaScript, and you build the game around the outside. So this downloads the model the first time you load it, caches it, subsequent runs are really fast. There was no load time for me right there. It would have worked if I was on an airplane. So how do we do this? How do we save it in Python? Depending on which, like how you're building your model in Python, if you're building it using the core TensorFlow API, like TF Core, you would export it using the save model. If you are already, if you already have a model and you're already using it somewhere else, like Cloud ML Engine or TensorFlow Serving, this is the exact same code. There's nothing special here about JavaScript, and this is the same format that a lot of the like TensorFlow models that we provide in the models repository and on TF Hub are already in this format. If you're in Keras, we're just using the save weights API. Really simple. Then we convert it. We take a conversion step to convert it into a TFJS format. Depending on which model type you use, you run this script. If you've installed TensorFlow.js, we've got a tool here for converting between model types. In this example, we're converting to a TensorFlow.js model, but if you've trained a model in the browser yourself and you want to convert it back to the Python format, this also works the other way. And then we load it up in JavaScript. Depending on where you're loading it, it comes in one of these places, 2 lines of code, load it up, and predict. Really simple. And the rest of it is just web dev. Now, I said that there was a conversion step there. Why do we have to do a conversion step to get into JavaScript? Now, depending on what you're using the model for, like in this case, we're only using it for inference, so there's a whole bunch of optimizations we can do to make it faster and reduce the model size. Some of these optimizations include things like pruning debug operations. Some graph subtrees can be converted into single operations. If we know, like if you've written like y equals wx plus b by hand, there's an op we can convert that to, and that saves a bit of model space. It allows us to hardware accelerate better. What else do? We convert things like trainable variables into constants and that kind of stuff. We also optimize the weight for browser caching. In some cases this means quantization, but this means that it saves better in the browser. And I mentioned that these are API compatible. That doesn't mean that TensorFlow.js does not compile the TensorFlow C++ API into JavaScript. It is all written from scratch, so it works in WebGL, and it's all custom JavaScript. What that means is that the API isn't necessarily, all of the operations that are available in TensorFlow aren't necessarily in JavaScript. Most of them are, all the big ones are covered. But the good thing is the source code is really well documented, the community mailing list is very supportive, and if you happen to run into an operation that isn't supported, it's quite easy just to write it yourself. Right, so here's an example of training in the browser. So, this is a live demo that I wrote the other day that predicts the mouse cursor. This was trained from scratch. I don't know if you can see my mouse here. Is that visible? Mm-hmm. Cool. So you can see I am moving the mouse cursor around, and the little mouse emoji is the prediction. This was trained in the browser. It's not training right now because it takes 1 minute or so to train. I didn't want to let you guys sit here while I spun the mouse around in a circle for 1.5 minutes. I didn't think that would be too interesting, so I've did it this morning. But if you want, we can we'll refresh it so you can trust me. So the dots just represent the data set. You can see it tries to guess where we are. And in the top right, we'll get some debug information. This is not trained yet. This is just the initial random init model. Then it very quickly, after a couple of epochs, starts to learn, starts to move back and forth, and eventually after about a minute or so it'll start to predict the mouse location fairly accurately. So what does this code look like? This is just view source in JavaScript. So data collection, how fast, what frame rate we want to collect the data at, how many frames ahead we want to predict. If we just predicted the next pixel, like it's not going to look like a prediction, it'll just look like a mouse cursor, so we need to send it off in the distance. And how many frames backwards into history do we want to use? This is a sequential model as well, using LSTM, and we just predict two things, right? X and Y coordinates of the mouse cursor. Stochastic gradient descent, L2 loss, save some metrics, train the model, this is some data prep, and then it's just model fit. It's a promise that we can use then when it's finished. Once it's done, we set another training run off. So this is online learning. This model is continuously training while we're using it. And then, most of this is all just data processing here, right? Drawing the dots on the screen. Then we want to make a prediction and update the little mouse emoji. Simple as that. And there's 112 parameters in that model, so this is 500 bytes. So if you wanted to keep a copy on the server and send it down, you can, that's a really cheap operation to do. Now, depending on where your experience is with machine learning, right? Like you could be here because you're a web developer who doesn't know about machine learning but wants to, or you're an ML expert that wants to learn about JavaScript. Learning how to write ML code from scratch can be quite hard. You might not need to train a model from scratch in the browser. I mean, you probably don't. So I thought I'd give some kind of example places to get started. So Adam mentioned TF Hub, which is a great place to download models from. We also have this TensorFlow model repository on GitHub, where we have dozens of like pre-trained models that are available to download. Some of them are good for mobile, some of them are a bit too big. So I've listed a few here that I think would be interesting to use. You've got MobileNet, plus the other image classification models that are pretty popular, like Resonant and Inception. Image generation. Has anyone seen the Edges to Cats model before? It's a model that generates a photo of a cat from a line drawing, like a sketch, and they're pretty horrific images that it comes up with, but that kind of like image generation model is available to use and download yourself. image to text, if you want to do image captioning. Object detection and segmentation is where you would, rather than putting in an image and getting out one of 1,000 categories, you put in an image and you'll get back a list of bounding boxes and labels of what things are in the image and where they are. Text extraction, you can do neural OCR these days, and then some fun like creative generation. This name ignizer model tries to generate human-sounding names and does a pretty good job. Text generation, there's a collab out there that was written by a Googler who that shows you how to generate Shakespeare text. So you upload a text file of like all of Shakespeare's plays, train it for 5 minutes on TPUs, and then you've got a model in Keras that's able to like generate arbitrary Shakespeare plays on demand, and like looks real enough. But they're all things you could like load up and pop into your models, into your apps rather. Browser-based machine learning in particular, I think, is going to get pretty big. Like we're not really seeing much of it around now, but I think it's going to be huge. So here are like if you're just stuck for something to do and you want to play around with some browser-based learning, I throw up some ideas that I think are going to be huge in the near future anyway. So browser-based machine learning doesn't have to be a web app; it can be a browser extension. I think there's a lot of opportunity for things like accessibility to be done through machine learning. Like you could imagine using like the image-to-text models to automatically add alt captions to images for like impaired users. And OCR is the same thing, right? Like reading what's inside an image. Content manipulation could be like a handy way of like avoiding censorship or blocking entire sites, like at schools, for example, where we could highlight, oh, this particular piece of content might be aggressive, or it might contain profanity or whatever, so we can hide it and just let them click on it once they've been warned. Privacy-preserving model training, I think, is a big place that browser-based learning is going to be huge. Like I said before, you don't necessarily want to handle users' data. You certainly don't want to keep it if you can avoid it. And so having techniques like federated learning or differential privacy allows you to train a model or incrementally train a model on a user's device, and rather than sending their data back to you, send their like the updated model weights back to your central location. Game AI or any kind of like, I guess even web AI. An example of where you might want to fine-tune a model. You might have a global model like the mouse cursor prediction that kind of predicts how a user behaves on your website, your shopping cart, and as a new user hits your site, get it to learn what their particular browsing habits are like, and incrementally get better and predict how they interact with your shopping cart, whether they're going to buy things or not. You can imagine for a game, something like that, where you get to the last boss, and the game has learned like how you play and can come up with like the perfect AI to destroy you. And then supplementing media codecs, right? Like we've already got models out there for JPEG artifact removal and super resolution. You can imagine cases where networks are user constrained by like network bandwidth or latency. It gets a low quality video stream or image sent down to them, and then you use like a local model to upscale it, give them a higher resolution, and remove artifacts. So there's just a few ideas I thought you could play around with if you want. If you want to learn more about TensorFlow.js, the website's really good. There's a whole bunch of fun examples up there. The source code's on GitHub, and this mailing list is really good. If you want to do any like feature development or you get stuck, you need some help, all the dev team is on there. If you want to get some of those demos, I've tweeted the mouse one earlier in the week, so you can follow me on Twitter. Otherwise, thank you.